Welcome to U.S. Preparatory's Radio Communications for the Prepper video series. This chapter is dedicated to frequency band characteristics, selection, and antennas. The purpose of the following video tutorials is to help preppers and the like be more aware and educated in radio communications, the options that exist, and to assist the average individual to develop a relatively inexpensive, far-reaching communication system with little to no experience in radio communications. This tutorial is to generalize certain aspects of the presented material without going into every possible detail, variable, or viewpoint about any given subject. Although there are what some might consider techie parts of the presentation, it is necessary to explain some of the finer details of the content and to help clarify the point. The viewer should keep in mind that the concepts and functionality of the presented material is the focus here, not the technical side of the systems or setup installations. The information within this video series are based on actual experience in both commercial public safety and amateur radio and may not always follow popular opinions. The series of videos have been made to enlighten, inspire, and inform the non-radio folk and help make the subject of personal radio communications more about independent, self-controlled systems rather than a community-based system that you have little control over. Working against nature is never easy nor cheap to achieve a task. Forcing things to be that aren't naturally meant to be is the way of the modern world, but just because we can doesn't mean we should. It's safer, cheaper, and far easier to move out of living in a floodplain than it is to try to stop the plain from flooding. Forcing a desert to be an oasis for the sake of residency requires far more resources to sustain it than building the same residence in an area that naturally supports it. This is also true with the natural characteristics of frequencies and how different frequency bands have very different traits. Choosing the best frequency range based on the natural attributes of these frequency bands can be made to work to our advantage, greatly reducing the cost of our systems and increasing the performance when compared to forcing a system to use frequencies that aren't up to the task. Here are some radio bands that you may be familiar with, shown as a reference with two very popular VHF and UHF bands. VHF high band consists of many subbands for many popular radio services. UHF also consists of many subbands for popular radio services. Although these bands tend to be the most popular and common for land mobile and the so-called public bands such as ham, GMRS, and MURS, many organized preparedness groups are looking for a solution to the restrictions that limit many group members from obtaining a radio license in the first place, some of which include a passing grade of technical exams as required for a license. Each group and family member would be required to hold his or her own radio license. The licensee's privileges dictate the radio bands available to them. Not complying with existing community lingo or operating practices is frowned upon. Unused repeater frequencies are scarce due to the oversaturation and band plan restrictions. No opportunity for exclusive group use of the frequency or channels. There is another option, however. A commonly overlooked frequency band that possesses near ideal characteristics for emergency preparedness use. VHF low band is more of a natural fit for local and wide area private radio networks because it offers so much more in the areas we need it, including these advantages when combined with the PEG radio licensing programs. No technical exams to study for. A single group license or call sign covers over 100 authorized users. Less line of sight means longer distances between stations. More distances between stations means larger coverage area and less infrastructure. Personal unit IDs, radio protocols, and procedures are set by the group, not by a community of outsiders. Frequency availability is plentiful, offering all channels necessary to build a robust radio network. Licensee or group has priority use of the licensed frequencies within 75 miles of the coverage area. Let's compare in greater detail the two radio bands that can be used within a PEG radio system. The UHF band, although popular, suffers from a few critical flaws, offering only fair performance characteristics in rural, suburban areas, especially when infrastructure or repeaters are not available. The line of sight between two UHF stations is critical for communications. UHF and higher frequencies are at a disadvantage in rural or suburban areas due to signal attenuation by foliage and other natural obstacles. UHF is short range when used direct and requires infrastructure for medium to wide area coverage. Higher frequency performance depends greatly on significant antenna height above average terrain. UHF systems cost significantly more than lower frequency systems due to the higher grade equipment needed to compensate for the greater signal loss. The UHF band is best suited for short-range, suburban and urban areas where building penetration and low sensitivity to noise is required. Here are a few great characteristics of the UHF band. Higher frequencies are not as susceptible to local noise caused by common electronic products. Smaller wavelength means smaller antennas. UHF frequencies are very efficient at penetrating man-made structures of concrete, steel, and glass. UHF equipment tends to be smaller than lower frequency equipment. UHF is an excellent choice for point-to-point linking of 2 or more fixed stations. The VHF low band also has its challenges. Although its assets far outweigh its vulnerabilities, there are a few shortcomings worth mentioning. Low band is more susceptible to receiving noise from light dimmers, low-quality chargers for electronics, and similar devices. Equipment tends to be a bit larger than higher frequency equipment. Low band frequencies are not as effective at penetrating man-made structures. Antennas tend to be larger than higher frequency antennas due to larger wavelengths of the frequency range. VHF low-band signals have the best performance outside dense urban areas and tend to be the best choice when longer distances are required with or without the use of a repeater due to these traits. Improved ground wave offers longer range when compared to a similar UHF system. Much less likely to be absorbed by natural obstacles such as hillsides, foliage, and trees. Antenna height above ground isn't as critical as UHF due to the longer wavelengths of this frequency range. Communications is possible slightly beyond the horizon or line of sight. Low band isn't required to narrow band, making older equipment still legal to use. More lenient rules and regulations allow for flexibility in developing wide area coverage radio systems. Lower frequency systems are less expensive than UHF systems due to less signal loss from feed line and antennas. There are always compromises in selecting a radio band, and not all frequency bands are equal, but a simple comparison between a few common frequency bands shows some facts worth knowing. Each band offers its own benefits and therefore has been chosen for a specific task based on these beneficial attributes. Comparing the yellow column of the VHF low band to the green column of the UHF band, both at 100 watts transmit power and 100 feet above the ground. At the same height above the ground, the lower powered 25 watt transmitter signal results in the same favorable outcome. Low band offers over 2 times more potential range than a similar UHF system. Being the best option for local long-haul radio, it's been chosen as the primary radio band for the Preparatory Emergency Groups radio system and licensing programs. You may be asking yourself, if lower frequency offers better range, why not use the HF bands? Well, once you go lower than 30 MHz, everything changes. Equipment costs go up, surplus equipment availability goes down, radio and antennas become much larger, requiring unconventional installations considered unsightly by many potential users, especially in a mobile environment. Most government agencies haven't used HF radio since about 1951 simply because it's not practical. This lack of widespread commercial adoption after this time period means HF equipment is rare and expensive. Not a great combination for low-budget preparedness groups. Most agencies replaced HF equipment with VHF by 1958. In 2017, the California Highway Patrol still relies on its VHF low-band systems for their primary communications. Although HF or high-frequency radio is necessary to providing another level of communication with ranges that exceed hundreds or even thousands of miles, the HF bands are not a simple push-and-talk form of radio. Relying on skip or atmospheric deflection in sideband mode, which isn't always reliable for local communications. HF is noisy by nature, requiring an attentive skill to operate, and demands an antenna that may be unacceptable to many.
Very good. Maybe Alan's pointing in your direction now. Yeah, for sure. Yeah, it's been a while for me. I mean, I've not been on 10 meters for a while here, Larry. Talking at this time of the evening, so I'm very glad we was able to make contact. I'm just going to put you there into the log, Larry, over.
In comparison, the Preparatory Emergency Group's radio system used standard FM land mobile radios for a more practical approach to local communications intended for every member of a preparedness group. The main focus of this chapter is exploring the best radio bands for local communication. Although the PEG radio and licensing programs do offer and practice HF radio communications as an interregional option, the primary PEG radio band resides in the VHF low band due to its lower cost, simple radios, typical installation methods, and reasonable antennas that generally result in a more acceptable radio system for the majority of group members.
1S1 to 586.
86.
So did you get an opportunity to check the vehicle for that item?
10-3. That's the negative on the item.
10-4. I'll search again over here. Thank you.
10-4.
Antennas are as vital as the radio and frequency band itself. To optimize performance, a little understanding will go a long way to increase the level of performance of your radio system. To understand some basic antenna requirements, we'll use this simple example of a battery and a light bulb. The positive side of the battery is what's doing the work, but by removing the negative or return path side of the circuit, there's no flow through the light bulb, therefore it won't light. This is similar for most antennas. If we look at a typical vehicle-mounted antenna, the whip of the antenna is its positive side. The negative side is the metal vehicle body surface it's mounted to. This provides the electrical ground connection or negative return path of the antenna system. The metal vehicle body also provides a vital necessity to most antennas, a ground plane. It's a metallic reflective area in proportional size to the wavelength of the antenna, which allow the radio energy emitting from the antenna to radiate towards the horizon. On higher frequency bands, such as UHF, the ground plane minimum is about a 1 square foot diameter circle and tends to utilize only the horizontal surfaces. On lower frequency bands, such as the PEG VHF low band, requires a much larger ground plane area, about 10 feet at 45 MHz, but the ground plane flows to the sides of the vehicle, making lower frequency antenna placement more forgiving than higher frequency antennas. The ground plane area has a dramatic effect on the antenna's radiation pattern. On higher frequencies, such as UHF, the ground plane area is smaller. As long as the minimum ground plane area isn't interrupted, the radio energy pattern will be near 360 degrees or omnidirectional. Placing a higher frequency antenna in a position that will interrupt its minimum horizontal ground plane requirement will cause a null in the radio energy pattern. Generally, higher frequencies are more sensitive to antenna placement, especially when the minimum required ground plane area is compromised. In the PEG radio band, since the ground plane area is far larger and flows to the sides of the vehicle, it makes these antennas much less sensitive to placement, but disrupting the ground plane by opening a door can deform or disperse the radio energy pattern, causing a null where the ground plane area is missing. Important with any low-budget radio system is getting the most out of the investment. To avoid common mistakes, a basic understanding of the antenna types and requirements is important. This information will impact the performance and efficiency to help you get the most out of your radio system. Lower frequencies contain longer wavelengths. This translates to a longer antenna. Higher frequencies contain shorter wavelengths. This translates to shorter antennas. The length of an antenna is calculated for the desired frequency. This is what allows it to be resonant on a particular frequency. A resonant antenna is an efficient antenna. There are standard intervals that an antenna can be resonant in. The basic three are full wavelength, half wavelength, and quarter wavelength. A full wavelength antenna is generally the largest version of an antenna that can be tuned for use on a particular frequency. Although the full wavelength antenna is super effective when tuned properly, its size usually forces other options, especially when used in lower frequency bands. A half-wavelength antenna is the most common antenna for the PEG infrastructure stations, offering a balance between size, performance, and durability. This design has no ground radials, making it rugged enough for sites exposed to high winds and weather, like tree mounts or mountaintop installations. The quarter-wavelength fixed antenna, commonly referred to as a quarter-wave ground plane, is generally the least expensive and the smallest of the three antennas made for fixed station use. This lightweight antenna is perfect for home base stations or temporary station use and performs well, especially when used in PEG radio systems that contain a repeater. For PEG vehicle installations, only the quarter-wave antenna is used. If the optional XTR or extended transceiver repeater is installed in the vehicle, you'll see two antennas: the PEG-loaded quarter-wave antenna for the mobile radio and the UHF quarter-wave for the XTR extender system. A quarter-wavelength antenna is the most popular antenna type for vehicle use due to its smaller size. In general terms, it's the smallest wavelength antenna efficient enough for most applications, especially vehicle and portable use. A quarter-wavelength antenna for the UHF band is approximately 6 inches. In contrast, the PEG low-band quarter-wave mobile antenna, tuned for 43 MHz, is 68.6 inches or about 5.5 feet tall. A more popular alternative to the 68-inch whip is the base-loaded quarter-wave antenna. The base-load coil makes up the difference in whip length, allowing the antenna to electrically remain a quarter wavelength while offering a smaller, vehicle-friendly antenna package. The same principles pertain to portable radios, but with exaggerated effects. It's important to understand why high-frequency portable radios compared to low-frequency portable radios with a stock antenna isn't necessarily an apples-to-apples comparison. Keep in mind, it's the antenna systems, not the radio, that causes these results. Recalling, a true quarter-wave antenna for low band is over 5 feet tall with the optional mobile loaded version to reduce its size. In order to achieve an antenna length suitable for a low-band portable, it must be drastically reduced in length to a mere fraction of its former efficient quarter-wave size. The lack of adequate ground plane area further reduces its effectiveness. In comparison, a true UHF quarter-wave antenna is about 6 inches tall. You'll see that the UHF portable radio antenna is not only electrically a quarter wavelength, it's also physically a quarter wavelength, requiring no reduction in length or loading. The metal radio chassis provides an adequate ground plane area, further increasing its efficiency. Despite this reduction in antenna efficiency, the low-band radio performs quite well. This is mostly due to the characteristics of the low-band frequency range. Ironically, the low-band radio itself is actually more efficient than the UHF radio and would offer more range if both antennas were equally efficient. The higher in frequency the antenna is designed for, the more bandwidth or usable frequency range it offers. Lower frequency antennas, on the other hand, offer less usable frequency range and is the primary reason why these antennas must be tuned for proper operation and efficiency. Wideband antenna models exchange wider frequency ranges with a drop in efficiency. Most wideband antennas are 20% less efficient than a standard antenna model and should only be used if absolutely necessary. To clarify why high-frequency antennas are usually pre-tuned and lower-frequency antennas are not, let's take a look at the PEG VHF low radio band and compare it to the UHF commercial radio band. Recalling that a lower-frequency antenna offers about 2 MHz of usable bandwidth, and the span of the entire PEG radio band is 20 MHz, it's impractical to produce a pre-tuned antenna for lower frequency bands, as there would need to be 10 antennas total to accommodate the 20 MHz span of this radio band, each antenna being pre-tuned to the center of its 2 MHz usable frequency range. Remember that a higher frequency antenna like a UHF commercial band antenna offers 20 MHz of usable bandwidth, and the span of the entire band is also 20 MHz, a single antenna can be used to accommodate the entire band. The antenna is simply pre-tuned at the midpoint of the band. Those of you familiar with CB radio might be confused at this point because pre-tuned CB radio antennas do exist. Unlike the PEG VHF low radio band, with its massive 20 MHz frequency spread, the entire CB band occupies less than 1/2 of 1 MHz. Therefore, CB radio antennas, with its 1 MHz of frequency bandwidth, can easily be pre-tuned to the midpoint of the CB band due to such a small frequency spread. Tuning an antenna with an SWR meter is especially important with lower frequency antennas, as the usable frequency range is less and therefore needs to be dialed in for efficiency. This meter shows the ratio between RF energy transmitted and RF energy reflected back into the radio. Reflected RF energy is not only wasted transmitter energy, but it also can be very harmful to the transmitter if the ratio is too high. The basic procedure for tuning a vehicle antenna is very simple. With the meter in the forward position, transmit while calibrating the meter to the cal line. Switch the meter to the reflected position, then transmit and observe the SWR. Trim 1/4 inch off the antenna. Switch to forward position, then recalibrate the meter. Switch the meter back to the reflected position, then transmit and observe the SWR reading. Repeat these steps to achieve the lowest SWR reading in antenna efficiency. An often overlooked and vital part of radio performance is the coaxial transmission cable. The type of coaxial cable, its length, and the frequency band that it's to be used in all have a significant impact on the performance of your station. Let's take a look at the anatomy of common radio-grade RG213 coaxial cable. The center RF conductor is where the radio energy travels to and from the antenna. The dielectric layer insulates the center conductor from the shield layer. The grounded shield layer's job is to contain the RF energy within the coax cable, and the sheathing is to protect the contents of the coax cable. The very characteristics that give UHF its great penetrating capabilities of concrete, steel, and glass also make it far more susceptible to signal loss before the signal even reaches the antenna. The smaller wavelengths of higher frequency bands can make it through the outer shielding fairly easily, making it difficult to contain these signals in standard coaxial feed line. This is why higher frequency radio systems require upgraded feed lines. This popular coax, when used with lower frequency bands such as PEG or CB radio, is efficient and low loss as it contains almost all of the radio energy. The results being only a 13.8% signal loss at 100 feet. With UHF or higher frequency bands, however, it becomes inefficient and lossy, especially with longer runs. The results being a massive 46.2% signal loss at 100 feet. The signal losses is so significant with higher frequency radio systems that the cell phone industry must use a 3-inch corrugated hotline coaxial cable in order to minimize the signal loss from a 150-foot run up the tower. Now for a chapter summary. Working with the natural characteristics of a frequency band offers more with less. The most popular radio bands aren't necessarily the best. Comparing the primary PEG VHF low band to the common UHF band potentially offers 2.5 times greater range. The PEG VHF low band is ideal for the long-haul portion of the PEG radio system, but not the best option for use inside buildings and structures. The UHF band is perfect for use inside structures and noisy environments, but far from ideal in regards to range, frequency availability, and natural obstacle absorption. The antenna placement and the ground plane is very important in a vehicle installation as it impacts the radio energy pattern and the antenna efficiency. How the 3 most common wavelength antennas are put to good use. Why lower frequency portable radios compared to higher frequency portable radios may not be equal. The usable frequency range of an antenna is determined mostly by the frequency range it resides in. Lower frequency antennas are rarely pre-tuned due to their narrower bandwidth. Why tuning your lower frequency antenna is vital to its performance. The grade of coaxial cable is important, but the radio frequency at which it's to be used in is equally as important.